Okay, so this is exponential families again. And in the end, so the thing that I was supposed to talk about, there's this stuff with semi-algebraic sets, and then he has a theorem which is that a certain exponential family is in a certain sense semi-algebraic. But this is a very strange theorem. Well, it doesn't say it's a theorem, but as far as I can tell, that's the purpose of this part of the chapter. But it's rather confusing because, firstly, to prove the theorem, the first thing you do is you unexponentiate. So you made this exponential family. The first step in proving the theorem was to take essentially the log again. So I don't really get why we did the whole exponential families business in the first place for this. And secondly, this thing that he states is semi-algebraic, it's actually algebraic. So in the end, I'm confused by the purpose of the chapter. But I think that we'll use the semi-algebraic stuff later. And anyway, it's kind of fun. So I'll do a little bit about semi-algebraic geometry sort of in general. And then I'll talk about I'll propose a definition for like a strongly or semi-algebraic statistical model, and then I'll write down this very easy example of these log linear models and prove that they are in various senses algebraic statistical models. And then, so that will be, and the proof is very easy and doesn't use any algebraic geometry, so it's nice, or at least essentially nothing. The proof is motivated by some theorem-mapped group rings, which I will also maybe state towards the end, because it's fun, but we don't need it. People were asking last time, like, how do we get finite generating sets for the ideals? And so Sullivan gives some examples, but I will give you a very general procedure which will always give you finite generating sets. And moreover, when you apply this very general procedure to Sullivan's examples, you get much smaller generating sets than what he has. So it seems pretty nice. I mean, I don't know how, well, I kind of know why his example, why he has more generators. But it turns out that you can do way better than he has. So, feeling pretty good about this. Assuming it works, we'll see. But first we do this semi-algebraic geometry. Or semi-algebraic sets. So maybe a brief reminder, if we start with some some set of polynomials in our Joan exponent x n, it could be an ideal or it could just be a set, it doesn't really matter. Then we define this thing which we call V of I, which is the set of, say, I don't know, P equals the points in Rn such that for all f in I of P equals 0. And so, we also define this over you can replace R with C or any field that you like, and it's still a definition. So we might say that S contained in Rn is algebraic if there exists an I such that S equals V of I. But this is not a very nice property if you look at taking images of maps. So later on today, when you look at these log linear or log affine models, then in some sense they're in a very natural way images of algebraic sets. But the problem is that images of algebraic sets are generally not algebraic. Of course, if you take the image under a really terrible map, this is unsurprising, but you could do something very reasonable. You could take, like, a circle, S is V of x squared plus y squared minus 1, contained in R2. So it's conveniently called S for circle, very nice. You can then take the projection map down to the reals, and the image is, of course, the closed interval from -1 to 1. And this is not an algebraic set. So we have this problem: if we start with something algebraic, we take a very simple linear transformation. The image is not algebraic. And the way that Sullivan is sort of proving his sort of theorem is, as far as I can see, that he proves that a certain subset is the image of an algebraic set. And so that doesn't make it algebraic, as we see in general. It turns out that in his example, I think it actually will be algebraic, which is confusing, but we'll come back to that in a second. But for the moment, we want to fix this. So what we're going to introduce is we're going to make a notion of semi-algebraic, and then this interval will be semi-algebraic. And so, in general, the images of algebraic sets will be semi-algebraic, and even better, the images of semi-algebraic things will be semi-algebraic. So it's a bit bigger than algebraic, and it is closed under taking images, which is kind of handy. So, So definition. So F and G contained in R join 1 up to xn finite sets of polynomials. So the associated semi-algebraic set is sometimes written B of f and g, basic semi-algebraic. So we're going to define basic semi-algebraic sets, and then semi-algebraic sets will be unions of basic ones, or finite unions of basic ones. So this is a set of points in Rn, such that firstly, for all f in f of p equals 0, and secondly, for all g in g, g of p is strictly greater than 0. So in other words, we allow ourselves not only equalities, but also inequalities of polynomials, strict inequalities. And so you could very reasonably ask, why do we take a strict inequality instead of a non-strict one? But it's more general to do this, because if you take the set where this is a non-strict inequality, you can write it as a union of the guy with a strict inequality and the guy with an actual equality. So this is the most general thing you could reasonably do. And so in general, S contained in Rn is semi-algebraic if it can be written as a finite union of algebraic, or basic semi-algebraic subsets. So the key example is now that the probability simplex is semi-algebraic. So the first thing maybe is that the interior of this probability simplex, the example is the G to the other way. The interior of this is semi-algebraic. It's basic semi-algebraic. And my equations will be something like f and g would be the set containing x1 up to xn. So we're just saying the sum of them is 0 and they're all positive. So nothing too surprising. So delta r n minus 1 itself, the probability simplex, is semi-algebraic, but it's not basic. To check that it's semi-algebraic, well, we quickly said that, well, it's less general to put strict, non-strict inequality, so that sort of should follow. More formally, if you want to be careful about this, you can write this as a union of 2 to the n minus 1 basic semi-algebraics. So roughly the idea is that, if you take, say, n is 2, then, so this is my probability simplex, and so I'm going to write this as the open interval union a point, union another point. So points are algebraic and semi-algebraic, and open intervals are basic semi-algebraic. So this generalizes. So I can always write it as a union of 2 to the n minus 1 basic semi-algebraic things. And so there's this sort of theorem, which is that images of semi-algebraic are semi-algebraic. But of course, we should ask images under what kind of map. If you take some random differential map, or continuous map, that's not enough. And so, for example, if you take projections from Rn to Rn, that's certainly sufficient. In the book, they talk a lot about the images of rational maps. So these are rational maps are maps given not by polynomials but by some rational function. So they're not defined, they might have some poles, so stuff goes to infinity. And they talk a lot about images of rational maps, which is sort of a slightly strange concept. But we don't need this theorem, which is why this is why I've not stated it too precisely. We won't use this today. I would like to prove a theorem that log linear models are semi-algebraic, or even algebraic. And so the question is, what does that mean? And so I'm going to try to write down a definition. It's not a great definition, but I think it's at least a definition which makes the theorem true, and we can decide whether we like it another time. To semi-algebraic subsets of statistical models. So I'm going to fix some data. So I'm going to let omega underline, this is going to be omega, and A, this is a measurable space. So a set with a sigma algebra on it, and M is a set of probability measures on omega. And I'm going to fix an integer and U contained in Rn. So in the book, I have the feeling that he'd like this to be an open subset of Rn, but then that is really inconvenient. So this is going to be an open subset of an affine linear subspace. So for example, it could be an open subset of Rn, but what I'd really like is that I want to be able to choose U to be the interior of the probability simplex. And so that's why I say it should be an open subset of some like translatable linear subspace. Because the idea is that U could be something like the interior of this probability simplex. And then I'm going to fix, so I'm still fixing stuff, I'm going to fix phi from M to U, this injective map of sets. And so, at this point, this is a sort of very, I mean, it's clear that you have lots and lots of choice of these things.
Sorry, what is an injective map of sets? Because phi is a...
So
sorry,
M is
a collection of probability measures.
M is a set and U is a set.
But why not just not say phi is a map from M to U?
Just because I want to, firstly because I'd like it to be injective, and secondly because I want to emphasize that I'm not at the moment assuming any extra structure on it.
Okay.
Like, because there are, like, I could put like some fun, I mean there's a whole business of like different metrics I could put on M.
Yeah.
And so my problem is that I don't know this story very well, or really at all. So it would probably be a good idea to, I mean you could say, well, let's put like one of these natural metrics on M and let's require that phi is continuous, or whatever. But then there's a whole lot of different choices of metrics. And so to avoid discussing this, I'm just going to say make a choice. If you make a bad choice, then the next definition will not be an interesting one, but it's sort of up to you. So I think, I mean, it's somehow like, in applications, there's normally a very natural choice of all of these gadgets. So the sort of running example would be something like, like one of these regular exponential families would provide you with all of this stuff. But I don't want to restrict to regular exponential families because that's not the setting in which we'll actually use it. And so, the definition, so we say a subset N of M is, and now there are a few options, so let's say it's strongly semi-algebraic, if there exists a semi-algebraic subset S of Rn such that N is just phi inverse of S intersection with N. And so, of course, this depends hugely on your choice of phi. If you choose some random phi, then that will change whether or not it's semi-algebraic. So you really should sort of fix the phi in advance. For example, coming from one of these regular exponential families or whatever.
S is contained in Rn, but M is a set of probability measures on omega. I don't understand.
Oh, I'm sorry. I should take. Maybe I've written this in a not good way. I should take. This should be U. I'm sorry. It should be a U, not an M. Yes, indeed. That makes more sense. So S and U are both contained in Rn, and then so their intersection is contained in U. I apply phi inverse, and that's contained in M. And so, well, so I put the semi in brackets because it's sort of obvious that you could delete the word semi in both places and you have a definition of an algebraic of a set, sort of being algebraic. So this is slightly different. So this isn't the definition that appears in the book. In the book they have another version, which is a little bit more complicated. which for today let's call weakly semi-algebraic. Okay, if there exists, so there's a few things now. S contained in R, N semi-algebraic, and V contained in Rn, again an open of an affine linear, and a diffeomorphism, say psi from U to V, such that, now I'll try to get it right this time, N is equal to phi inverse of psi inverse of V intersected with S. Okay, so this is the definition that's given in the book, or at least this is this seems to be what the definition in the book is saying. There should exist such a diffeomorphism. So I find this, I mean, it's a little bit like, it's quite hard if somebody gives you, so if somebody gives you the data on the right hand side, it's maybe quite reasonable to try to decide if it's strongly algebraic or semi-algebraic. To decide whether it's weakly semi-algebraic is kind of awkward because you have to quantify over all possible diffeomorphisms to all subsets of all copies of Rn. So I don't like this definition very much. I write it because it's what's in the book. The theorem we prove will be about the first definition. So like, if you don't like this, it's fine and you should just ignore it. But I'm writing it because it's in the book, or the notes rather. So obviously if you, like, the question of like, does there exist, so if you give me some m, and if you give me the m and the n, the question of does there exist a phi such that it becomes semi-algebraic is a terrible question, in as much as it's just a question about cardinalities. But the idea is more that there should be some natural choice of phi, like coming from one of these regular exponential families, and then for that natural choice of phi, you should ask whether or not this thing is strongly or weakly semi-algebraic. And then of course in reality there might be more than one natural choice of a phi. So if you take this discrete example, this like finite discrete example, so omega is a finite set, then you can view it as a regular exponential family as we saw last week, and then U will be the whole of Rn, and n is this cardinality of omega. But you can also take, like, you can take U to be the probability simplex in Rn plus 1, and that also works. So like, for any given sort of practical statistical model, there can be multiple different reasonable ways of building yourself one of these phi things. And you'll get different, and then the question of whether it's algebraic will be different depending on the choice that you make. Reasonable, like, it's a definition. So what I want to do is so last time we saw these log linear models, log affine models, and so I will recall a little bit what happened, so I just want to focus on this one example, this log linear example, and I want to write down, then there are sort of, well, I write down the omega and the two natural choices of phi, and then I'll show that one of them is actually strongly algebraic and the other one is weakly algebraic. So let's try to do that. So, I mean, I guess it's I think for statistics people this must be very trivial because I'm only looking at like discrete, I'm only looking at a case where omega is a finite set, which I can't imagine is very deep and interesting for statisticians. But it seemed that, well, to me it was very helpful to try to like write down exactly what Sullivan was saying in this case, and it took me a little while to work out. So that's what I will do. So section 3 is the discrete case. So let's say omega is just a set from set of 1 up to R, and the measure is just going to be the discrete measure. So my sigma algebra is just the discrete one. And I'm going to let n be the set of all probability measures on omega. Such that for all I p of I is strictly greater than 0 for then measuring p. So we saw last week that Amini gave us a way to interpret these discrete families as regular exponential families, but we saw that this interpretation only worked under this assumption, I think. It sort of went wrong, like the formula didn't work at the boundary. And so I'm going to impose the same assumption here, and that will actually make life much, much easier later on in the talk as well. So I'm a big fan of this assumption now. It will simplify things a lot. And so the idea is that n is going to be a subset which is going to be some log affine model, so I'll record in a moment what that means. But for now, we should talk about like the two reasonable possibilities, or at least two reasonable possibilities for phi. So one of them would be the sort of simplex version. The first option is the simplex option. So here I'm going to take n equals r, and u is the interior of the probability simplex. Am I doing this right? And so phi, I think you can guess. So this is actually a bijection, and I'll send p goes to the vector p of 1 to p of r. So that was a bit boring. Let's do another one. So I don't want to, what am I going to do? What should I delete? I'll erase this bit. So the other version is the sort of the exponential one, which is what was described last week. I think I'll try to leave, because this is the thing I'm about to instruct, so let me not erase it just before I write it down. Or even, no, it'll fit. I'll just write it smaller and it'll fit here. I'm sorry, this is poorly planned. So the exponential option. So I'm going to, you already told us how this worked last week. So, but I'm just going to write it down briefly. And I'm going to write it in a way which will somehow make it fit with these definitions. So here I'm going to take n to be r minus 1, and u to be the whole of r minus 1. Sorry, not subset, u equals this. Because my map is only injective, so if I have a u, I can always choose myself a bigger u. So no harm is done. And then I've got myself, I'm going to define a map f from r minus 1 to this interior of this probability simplex, and I'm going to send p1 up to pr minus 1. It's going to go to, okay, so now this is just the sort of, you have to just fiddle around to make it actually work. So what should I do? 1 over 1 plus the sum from I equals 1 to r minus 1 of e to the pi, so it's a p times the vector e to the p1 up to e to the p r minus 1, and then I'll stick a 1 at the end. So, like we know that somehow the r to the r minus 1 is diffeomorphic to the interior of the probability simplex, and this is just writing down some diffeomorph. So it's a smooth map whose inverse, it's a smooth bijection whose inverse is also smooth. So, and then what am I going to do? I'm going to define phi prime. It'll still fit down. This is going very well. Phi prime. I'm just going to define this to be f inverse converged with phi. And this will go from m to, maybe I should call this u prime, just for the sake. This will go from m to u prime. So again, I've got myself an injective map of sets. And it's these, it's sort of, the only difference between these is that I either compose or don't compose with this diffeomorphism. And so what we're going to do is we're going to say that actually these log linear models in the simplex parameterization, they're strongly algebraic, and therefore as a trivial consequence with the exponential parameterization, they're weakly algebraic. So it's a bit silly, but it's true at least. So, okay, let's recall these log linear models. So I'm going to stay in this discrete case. So I'm going to keep my same omega, and I'm just going to have my phi and my phi prime. And I'm going to now define an n, and we're going to discuss whether this n is semi-algebraic or not. Okay. So I'm going to first choose a. So this is a k by r matrix. And I'm going to assume that the vector 1 is in the row span of A. So this this assumption is required for the sort of statistical side of the story. This assumption was quite important because it meant that there existed these normalizing things. Actually, this assumption will not appear again. I'll never use this assumption in what I'm going to say. So it's a bit strange. I don't actually need this assumption, but it's otherwise. If I don't have this, I think I should not call it a log linear model. Okay, so a definition of a log linear model. Associated to A. So, how do I want to write this? I'm going to call it N or NA, sometimes I emphasize the A, and this is going to be phi inverse of the set of P in the interior of my probability simplex, such that log P is in the row span of A. So here P is a vector of length R, so when I apply log to the vector, what I mean is apply log to every component of the vector. They're all conveniently positive real numbers, and so log is a legitimate thing to do when I still get actual real numbers. And I just require that those live in the row span of A. And so, if I remember correctly, last week there was a thing called H, which was some positive real valued function. And I've left it out because I think last week we argued that we could, if we had polynomials, if we had an algebraic polynomials cutting out this model, then by scaling by H we could get polynomials cutting out the other model. So just to make life simpler, I've let H be the constant function of 1 because I can. So this is the log linear model. It's some subset of this set M of all of my probability measures with sort of a non-zero value. And so the theorem, which I will give a name to, it's the only theorem I think, but there will be a lemma too, and I will refer to that. So with phi the simplex parameterization, the subset NA of M is strongly algebraic. So what this means, sort of unraveling the definitions over there, is that we're going to find some actually algebraic subset of Rn, we'll call it S, whose intersection with this probability simplex will just be the log affine model. So in other words, what we're going to do is we're going to write down sort of equations for this log linear model inside the interior here. And so this has a sort of and so we'll prove this in a moment. This has a sort of silly corollary, which says that with phi prime the exponential parameterization, the set, say NA of M is weakly algebraic. And so this is sort of a complete triviality because like phi prime was defined by composing phi with a diffeomorphism. And so to get this thing, you just undo the diffeomorphism. And so like essentially nothing happens. The reason I'm stating this corollary is because this seems to be what Sullivan is saying in his final section. The corollary seems to be Sullivan's sort of result that he's claiming, if I've understood what he writes correctly. So, but I mean, it's nicer to prove the stronger, so the first thing is both stronger and easier, so let's do that. Okay, so yeah, I'll spend most of the rest of my time, I think, proving the theorem. And so
last time we had an ideal defined in terms of A.
Yes.
And we also had a model defined in terms of A.
Yes.
And it was never clear whether the vanishing set of the ideal was the same as the model. And this is this theorem.
Yes.
So this is filling in the gap we had last time.
I hope. Yes, indeed. That was
You hope.
And so also the theorem just says that there is an ideal, but you should also naturally ask, like, can we find a finite set of generators?
Yes.
And so that so we'll prove slightly more. We'll give an algorithm to write down a finite generating set, and it turned out to be easy, like really, really easy. It's kind of strange.
David,
Yes.
Sorry, I think you mentioned it, but I've already forgotten. So assuming we have a strongly algebraic n in n,
Yes.
then we have this diffeomorphism. Why do we know that?
Sorry.
Yeah, it's good. That we can once again find an S in Rn such that the intersection with the image is.
We don't. So being strongly like well, sorry, how do we know we can find a diffeomorphism? Like we just take it to be the identity from UT. Like,
Oh right, of course.
If you're weak, if you're strongly, then you're weakly because you choose V equals U and phi is the
Sure,
identity.
yeah.
Phi is the identity. So yeah, that's okay. So it's good. I've called one strong and one weak, and strong and twice weak. It's reassuring. But strong is crazy. Like why would you want strong? So I was a bit confused because he gives this notion with the diffeomorphism.
So you say, why would you want strong? Because it's true? No, so it's nice.
Yeah. Also because I find the weak version with there exists a diffeomorphism, it's a bit, I don't know. Well, mostly just I prove strong because it's true. So Sullivan defines the weak version and then he gives 3 examples. But one of them is the example which I'm currently stating, where it's actually strong. And the other one I think it's also strongly semi-algebraic. And the other one, I don't think it's either of them. Like, it's not really clear what the third example is an example of. I mean, not clear to me. I'm sure he understands this very well, but I was a bit lost. So I don't have any non-trivial examples of the third option. Like my examples of like the weak version all come by proving the strong one and then applying some like random diffeomorphism to it.
Because he meant to say, why would you care about weak, right?
Yeah.
So you can just say,
Yeah.
why would you care about strong?
Oh, I'm sorry. I just misspoke. Yeah, indeed. Like, I mean, it could well be that there are really like. I mean, it's sort of a strange question, but it always comes down to this choice of parameterization phi in the first place. So if you have a weak one, you can always choose a different phi such that you have a strong one. And so whether you want to think of it as a choice of a phi, like making a clever choice of phi, or as applying a diffeomorphism, is, I mean, so like they're sort of the same question. But right, in the examples that we've seen, we always have the strong version. So let's prove that. So let's write down a map. So we're going to have a map which is going to be called phi superscript A, capital Phi superscript A, which is going to go. So this is Sullivan's notation when it goes from. This is actually not Sullivan's notation. I'm lying. I'll explain why it's not in a sec. And so what's this map going to do? If I take some theta in here, I'm going to send it to the product from I equals 1. I try to get my k's and r's the right way around, but I may have failed. Okay, so A is the matrix like A. The entries of A are a little a I j, and so so theta is a vector of non-zero real numbers, and then in fact, also not, no, maybe you can just greater than 0 with that, right? That's even nicer. Because I don't know what's the square root of a negative number. It's not a good question. So I take some vector of real numbers of length k, and then I produce the jth entry. I'm going to produce a vector of length r, and the jth sort of term in it is going to be given by just like multiply together all of these theta i's, and the exponents given by the aij's. And so oh no, star is, I'm sorry, yeah, I'll come back to z.
So is this the same as the multiplication by A composed with the log map?
Yep, exactly. So the star is fine. I'm sorry. These are we're not taking square roots. These are all integers. So there are no square roots happening. We're just like taking 1 over stuff, and that's fine. We're only going to use it on the positive real. So if these were not integers, if these were like a half or something, you could just restrict to the positive reals, and it would still be fine. That's a good one. So Sullivan defines this on the whole of Rk to the whole of Rr, and then it's a rational map, so it just fails to be defined in some places. And you can do that. I mean, you can talk about partially defined maps if you like, but we're only interested in what happens on the probability simplex, or sorry, on the interior of the probability simplex, and that's contained in this R star to the R thing. And so we can make our lives a lot simpler by just not worrying about what happens when the variables are 0. So let's make our lives easier. And later on it will allow us to do everything in terms of group rings instead of monoid rings, which will make life way easier. Okay, so I'm going to think of my A, you know, I'm not supposed to, but I can think of A as being like a linear transformation, right, from Z to the R to Z to the K. So I'm teaching this like linear algebra for computer scientists, and I spend half my life telling them off, no, a matrix is not the same as a linear function. I spend the other half of my life saying, oh, it's just a linear function. So I'm sorry, but what can you do? And I'm going to write K is the kernel of A, and if you like, this is just the null space of A. Sorry, no, it is the null space of A. It's the orthogonal to the row span of A. And so this is, in some sense, all that you really need to prove the theorem. This is the sort of the most non-trivial step in the proof of the theorem, in some sense. So let's have ourselves a lemma. So this will be lemma 2, because we had theorem 1, and this is somehow the easier to find numbering convention. Okay, so let E be a generating set. Okay, and let P be a vector in R greater than 0 to the R. Okay, so you could take B to be the whole of K. That's a fine thing to do. There's an example of a generator. So we're generating as an abelian group. So you could take B equal to the whole of K, but also because Z is a nice ring, you can always find a finite generating set. And there are algorithms to do that, which we'll see in a little while. And so like taking B to be a finite generating set will give them more interesting answers. And then the following are equivalent.
Sorry, so what do you mean by generating set again?
Just as an abelian group. So every
So you
What does that mean?
restricted your coefficients now to integers, right? Because here you said 1 is in the row span, but that was maybe using rational coefficients, who knows?
Actually, I don't know. That's a really good question. So when we say 1 is in the row span, do we allow rational coefficients?
Well,
I don't know. Perhaps we probably.
if you allow me to multiply A by 5 or so, then you will have to
No, I agree
allow
they're not
rational.
equivalent. I don't know what the correct. I think that being in the rational row span would be enough for the statistical
Okay.
application thing. That's a really good point. So I guess on the left-hand board, I'm always taking like the integer versions of things. So K is really a subset of Z to the R. And so giving an algorithm to find K, it's not as like finding the kernel finding the kernel inside Q is you just do Gaussian elimination. To find the kernel inside R, you have to be a little bit more careful, but there are like standard algorithms to do this. And it's not
But generating set just means that you can write everything in the kernel as a sum of those things, right?
These algorithms even give you a basis, right?
Yes.
The set basis. Yeah.
Yes.
So
But what's the difference between the generating set and the basis then?
independency.
Okay.
Yeah. So it doesn't
Or
like,
minimality.
yeah, indeed. So I mean, you could choose a minimal B, but you don't have to. Oh, when you say basis, do we? Yeah, it is free. Indeed. So there are algorithms which will give you a minimal generating set, and
The basis.
yeah, also known as a basis.
It's not the same.
Ah,
Of a set.
yeah, true. But yeah, so sort of you can always find there are definitely algorithms to. Well, firstly, there's an algorithm which is take B equals K. If you want a finite one, there are algorithms to do that. And if you want a minimal one, there are algorithms to sort of find almost any kind of B that you could reasonably ask for. In the examples we see, then it will be very, we'll find some B's and it will be very easy in the examples that we do. So anyway, what following are equivalents? The first one is that so log of P lies in the row span of A. Interesting. So do I mean the rational or do I mean the integer row span of A? I think here, what do I mean?
Real, probably. Right?
Real row. I must mean the real row span
I
of
think
A.
real.
Good. Because otherwise it would be very unlikely to work. The next one is that P lies in the image of this phi a that we defined up here. And the third one is that for all okay, so if I choose an element of this kernel, then I require that p to the k is equal to 1. So what do I mean by p to the k? This is, by definition, the product from I equals 1 up to r of p I to the k. So this is really a real number. A positive real number. And the third one is that for all it's the same condition, but where I only check it for things in my generating set. And so I've called it 3, maybe I should call it 4, that would be more natural. It comes after 3. And so this condition 4 is sort of the useful one, because this will really give us like essential, so this will, after a little bit of playing around, give us finite generators for the ideal that we're looking for. And so, let's see. So some of the implications are easier than others. So let's do them in a sort of sensible order. Maybe I'll do the easy ones like this bit. So we can do a quiz. Okay, so let's do 1 implies. So I find it a little bit, like, because people come from many different backgrounds, I find it hard to know which steps I should say, oh, this step is clear, and which steps I should prove things. So I'll err on the side of proving everything, but if everyone thinks they're obvious, then just shout at me and I'll skip them. Because
It's hard for us to know.
Pardon?
It's hard for us to know what everybody thinks.
No, but if
Everybody shows up, please.
yeah, maybe you should all, like, who would like me to prove 1 implies, like, who thinks this is worth doing?
Yeah, I'd like to see one.
Okay, 1 implies 2, let's see what happens. Let's see if it's true. So say, let's write log p. Remember this is a vector. Let's write this as the sum from I that equals 1 to k of lambda I times ai. These a and I are the rows of a, and the lambda I are real numbers. So yeah, it looks like I'm taking the real roots now. So then p, well, so if we, like, this is a statement about 2 vectors, so if we write it out sort of explicitly,
Oh, yeah.
well,
Sorry, just teasing for a second. You said, oh yes, it is up here.
no, I agree. But I had to write it down to be committed as well. So this is just the sum of I equals 1 up to k of lambda I a I j. And so if I exponentiate both sides, I find that pj is just e to the lambda I to the power of a ij. And so p is equal to phi. Oh, thank you. Yeah. Product over I of this thing. So this is just phi a of the vector of e to the lambda 1 to e to the lambda k. Okay. So nothing very much happened. I think we can believe that 2 implies 1 will go similarly. If we write p as phi a of something, then we can always assume that the some things are positive because p was positive. So if there are any negative ones, just replace them with the positive ones. And you must always have an, yeah. So I guess there's some care to be made with the signs. But if p is an image, then it's also an image of the positive part. And so then I can just apply logs to, like, whatever the thing is that maps to p, I can apply logs to it and I'll get these lambda i's which I wanted. So this thing will be the linear combination.
But after taking the log, this is all linear algebra 1, right?
Yep. You mean the whole proposition or just this statement?
Part of
I think the whole thing, in fact.
the whole,
I mean,
this
so
whole
it's,
thing?
yeah, but that's okay.
No, which whole thing?
The whole of the lemma.
Yeah, I think the whole
Yeah, indeed. So this is basically like linear algebra 1, take log of linear algebra 1. But one has to be a little bit careful with the signs. Yeah. So 2 implies 1 is similar. So okay. it's the image of something. Assume that something is positive, take logs, and you get the lambda i's that you wanted. 3 is equivalent to 4. This is easy. A generating set from my kernel. So the interesting bit is somehow that 1 is equivalent to 3. So let's say 3 is equivalent to saying that for all kappa in the kernel, p raised to this thing is 1, that's the definition. This is equivalent to saying that for all things in the kernel, I apply log, and log of 1 is 0, but this is just a sum from I equals 1 to r of kappa I log pi. So this is equivalent by what we said here to saying that log of p lies in the kernel of a orthogonal. Well, sorry, no, this is just a statement that log p is orthogonal to the kernel, and this is by our equality here is equivalent to saying that log p is in the row span. Okay. Yeah. So fortunately, so I realized that I wasn't careful enough about whether I was taking the real, so here, like, do I mean the real or the integral row span? And so here I clearly mean the real row span, but here I mean the integral kernel. But fortunately, the orthogonal complement to the integral kernel is the same as the real row span. So I wasn't careful enough, but it still works. Because the real kernel spans the, sorry, the integral kernel spans the real kernel. So its orthogonal complement will just be the real row span. Phew, so I didn't make a horrible mess. So the lemma is done. And from the lemma, we're going to prove the theorem, and hopefully this will be enough space. So let's do that. So in some sense, we're sort of done, in as much as we've got so this expression is giving us a whole bunch of, or even if you prefer this one, this is giving us a finite set of generators for some ideal. The only thing we have to be a little bit careful of is that some of these kappa i's may be negative. And so, like, this isn't an ideal in the sort of usual polynomial ring, if you like. So that's sort of easy to fix. So what are we going to do? So let B generate the kernel of A. For example, we could take B to be equal to the kernel, and then for each B in B, I'm going to write an equation FB is going to be the polynomial and so this is almost a polynomial. Maybe the best way to think of it is that it's a polynomial so this is, so I take the polynomial ring in x1 onto xr, but I also adjoin the inverses of the xi's. I can just do this formally. I can just like basically allow myself to include 1 over xi as a variable. This works. This is no problem. Notice that this is still not a field. So something like 1 plus x1 is still not invertible. So x1 has become invertible, but 1 plus x1 is still not invertible. So this isn't a field. It's just like a slightly bigger polynomial ring in some sense. Okay. So you can make so we think of, if we don't have the plus or minus ones, we think of these as being polynomial functions on r to the r. With the plus or minus ones, we can think of them as being polynomial functions on r star to the r. So this is like polynomial functions. And so you can make a parallel notion of algebraic subsets of r star to the whatever you want, and then they will be cut out by polynomials that way you allow these inverses. And so, in some sense, what we've seen is that this log linear model is algebraic, is sort of R star algebraic instead of being actually algebraic. So that we've proven so far. But the theorem claims that it's actually algebraic. So let's do that. So let f be prime be so fb prime is going to be essentially the same thing, but I just clear the denominators. So this is now an actual polynomial. And then the thing which one has to check is that so the zeros of f b prime, sorry, f, supposed to be, the prime is on the f, I'm sorry, it's not on the b, in r star of the r, equal the zeros of f b in r star. So in other words, as long as we only care about positive or non-zero real numbers, then it doesn't matter which form of the equations we take. Okay, so now I want to finish proving the theorem. I will use the lemma, so maybe I'll get rid of this board. So, theorem continued. So I'm sort of heading up here now. Okay, so then